Hi everyone, welcome to this week's Crunch seminar. Today we have two talks. The first talk is on stochastic pins, deep learning solvers for SDEs. This talk is given by Marcin Baranek and Professor Paweł Przybyłowicz. Professor Paweł is a full professor of mathematics working at AGH University of Krakow, Poland. His research interests focus on the computational complexity of stochastic and deterministic delay differential equations and Monte Carlo simulations. In particular, he is seeking optimal algorithms within the information-based complexity framework to approximate solutions of SDEs with jumps, as well as efficient implementation of these algorithms and Monte Carlo simulations utilizing GPU graphic cards. He also studies the relationships between the theory of stochastic processes and machine learning. He is the recipient of 2 international awards for scientific achievements, Information-Based Complexity Young Researcher Award in 2012 and Joseph Traub IBC Award in 2018. He has about 15 research projects in academia and industry and has 50 plus scientific publications and is an associate editor of the International Mathematical Journal, Journal of Complexity from Elsevier. Marcin Baranek is a third-year PhD student at the Faculty of Applied Mathematics at AGH University of Krakow, Poland. His research focuses on the application of deep neural networks to the approximation of stochastic differential equations, with particular emphasis on high-dimensional problems. He also participated in an industry research project where he conducted research involving the use of stochastic differential equation models for forecasting electricity demand, production, and prices. With this brief introduction, I invite both Professor Paweł and Marcin to start the presentation.
Thank you very much. And also, we both we would like to share our deep thank you, for being invited here and to have the opportunity to share with you with some recent progress about stochastic pins. And I will stop sharing my screen because as I told you before, I have some lags during when I'm talking and presenting. So I hope you can hear me. I hope you can hear me.
Yeah.
Okay. Okay. So more or less, the presentation will be like this. I will start with the theory. Give you the framework about the stochastic version of the physics-informed neural network. And then after 20-25 minutes, Marcin will say something about the implementation part of this project and some numerical results. Let us start with the problem statement. So we are dealing, for now, we are dealing with stochastic differential equations driven by additive Levy noise, okay? So we have here the drift term, here is the drift term, here is the diffusion term, and L can be the Levy process. Under, of course, some suitable assumption on the finite on the number of jumps in the finite time. Some technical assumptions on this are in this preprint. However, in this talk we focus only on the m-dimensional Wiener process, because in order to give you all the details, it will take too long, and probably won't give you this general overview. For us, it's important to give you this general overview, and also this Wiener case process is as we can see, very informative, and also give insights about the case of additive Wiener process, and also some insight how to switch from this case, which can be seen as particular case, because yes, that's true, to the general case when also this diffusion coefficient depends on the solution. So to the multiplicative noise case, we can say. Nevertheless, the questions are as follows. One of many, we can say. One of many questions that we would like to answer. For now, main 2 questions are: is it possible for the artificial neural network to learn or approximate stochastic dynamics? Okay, because all of us remember that neural networks are the deterministic systems. Fundamentally neural network deterministic systems. So what we would like to approximate in order to have some black box that approximates stochastic dynamics, okay? And we'll give you answer for this. And also the second is, can neural network can efficiently approximate trajectories of the underlying SDE? But remember, this is, we can say, the work in progress and the initial part of this project, we can say, about the stochastic pins, stochastic version of the pins. And so the aim is not to have, because it's similar like for the pins, yeah? We are not aiming at having better, in general, numerical methods for solving, approximating, at least in small number of dimensions, that's true, to have better approximation schemes than the natural one, Euler, Milstein, Wagner-Platte, and so on, okay? This is true. You will see from the numerical experiments that we can train neural networks in order to approximate the solution of stochastic differential equations, but this is not the aim, okay? The aim will be something similar, we hope, like for the pins, to solve the inverse problems. In this case, stochastic inverse progress. But the stochastic inverse progress are really work in progress. Yes, inverse problems are work in progress. So we are not talking about this, but to give you the aim, yeah, it's similar like for the pins with this extension about the stochasticity. And problems you'll see start from the beginning because of the stochastic nature of SDEs. When we are dealing with SDEs, as far as you remember, the solution is stochastic process. So every stochastic process has infinite many trajectories, solution trajectories, okay? Not like in the deterministic system that when we have only one trajectory for the OD, PD, whatever. In the stochastic case, we have to deal with this large, infinite amount of possible trajectories of solution of SDE. Okay, and if you will be, I hope, more interested about some technical details, this is the preprint, still work in progress. Recently, we posted the second version of this preprint. We extended also either the theoretical part, some theorems, and also the numerical parts. And we see that we have another amount of materials which will be added probably in preprint version 3. So keep in touch. And of course, starting, so all of you know this seminal, very important paper about which were introducing the physics-informed neural networks. And we would like to do it, this as stochastic pins, also in this fashion, okay? Because on the next slide, we have some works that also try, or not only try, that use some neural networks to approximate solution of SDE, but in our opinion, they are in different fashion. You can also check this. Not in this direct fashion like in pins, when we are directly defining the loss function, which we would like to minimize in suitable way, and for which the minimizer will be the solution. Okay, and so here are some no results for the case when we are using artificial neural network to approximate SDEs. More or less, these papers are in that fashion that we are approximating the driven Wiener process with some simpler process, and then somehow define suitable loss function in order to minimize it, okay, and have some approximation of the process X. Also, in this spins was used in some the shortcut. Yes, spins was used in this paper. However, this is not also in our opinion, but you can check, as I told you, not in this fashion, because main drawback of this approach is that you have to know many trajectories of dynamical system, which in particular is not possible in a real dynamical system. For example, imagine you are trying to use this approach of spins to the inverse stochastic problem, in order to have some parameter estimation for real stock prices. Okay, you have only one history. So this is nice approach, but for us, rather from the theoretical point of view, because also they are approximating something like the covariance structure of the problem. So not direct approach. And you can also check the other ones. there are some also defined, defined some loss functions, of course, but as I told you, and I hope convince you during this talk, not in this direct way as it was in this paper, when directly minimizer of some loss function, nonlinear, highly nonlinear loss function in infinite dimensional space, which we would like to approximate in finite dimensional one, then we have this approximate solution of the initial PD, OD, and in this case, also the SDE. Okay, so let us go to the math. Some assumptions. We started from the classical one, classical assumptions for the stochastic differential equation. Yes, to have some theorems, yeah, and because this is, it seems like, and probably also it's true that it seems that it is very new topic in this case when we would like to settle this pin approach for the stochastic version. So we tried to do it in a rigorous way. But yes, to do it in a rigorous way is very hard mathematically. So we thought, okay, let us start also with the classical assumptions. The classical assumptions for SDEs are of course the Lipschitz case. Okay, so we are assuming that the drift coefficient is globally continuous, and also Lipschitz continuous with respect to the space variable. But for now, you have to believe me. But we have some preliminary estimates that shows that we can lower these assumptions. Okay, so we can go to the some local ones, one-side Lipschitz, and so on. But this requires, of course, again to prove all the theorems proposition that I will show you here. Okay, so we are focusing now for the Lipschitz case, yes, the classical one, but you can extend it. You can go outside the Lipschitz assumptions. And there's sigma, the diffusion matrix here is the D times M dimensional. The initial value is deterministic, but this is without loss of generality. It can be also random as in a normal SD, but this is irrelevant here. And so first very important thing in order to formulate it, because the aim is like this. You have to reformulate the problem of solving the stochastic differential equation in the fashion of minimization problem. Okay, what we have to minimize, and what will maybe how we have to define the loss function in order to obtain the problem that yes, infinite dimensional problem. That's true, infinite dimensional minimization problem. But which solution will be the solution of our SD? Okay, so you know this for the OD, you know this for the PD, and for this deterministic is more direct, okay, as you will see here. For the SDEs, starting from the additive noise case is not obvious, okay, because the problematic case is all, of course, this diffusion part, okay. And I'm also giving you here the case when sigma is not dependent on time, but you can check almost directly by having some additional Euler approximation. We can also consider here sigma depend on time. And also this transformation, which is a particular case of Doss-Sussman well-known transformation, can be applied exactly in the same fashion and have this extension and have this approach, and have this approach well defined from pins to stochastic pins. But unfortunately, if you ask me about sigma depending on solution, then this Doss-Sussman transformation is not as direct as here in this case, and this is work in progress. Okay, so I will not give you answer what we need to do in the case when sigma depends on a solution. Okay, that's why we started with the additive noise case. To have it rigorously, defined well, the algorithm and also the theoretical part. And why we use the Doss-Sussman? If you know that Doss-Sussman for SDE, this is very nice and classical connection between stochastic differential equation and random ODEs, random ordinary differential equation. Okay, because something from history. Originally, when Ito developed the SDEs, he wasn't thinking about the connection with ODs, okay, or random ODs. It was different currents in mathematics, the different domain, we can say. But Doss and Sussman try to answer this question. If we have some more connections between SDs and ODs or not, because for example, trajectories of the initial SDE X of trajectories X are nowhere differentiable, okay? Nowhere differentiable. If you are considering here Wiener or general Levy process, these trajectories are in general nowhere differentiable. There are, of course, some particular cases, for example, when you are dealing with the Poisson case here, okay? But Poisson is very particular. And for general Levy process, you don't have differentiability of X. And but from the solution of random ODE, in general random ODE, if you forget about W, you can have random ODE like this. Y prime is f of t, yt, and f can be random field. F can be random field. Here also is a random field, but the particular random field, okay, of the particular form. In general, right-hand side of a random ODE is a random field. Not only random process, it's a random field. And so the question is, maybe you have some connections because Y is differentiable, X is not direct. But in this particular case, this is direct transformation and very well known and easily established. When you are taking X, subtracting the sigma w, you are arriving at random ODE, and the process Y is continuously differentiable, okay? And F is explicitly given in this form, A of t, Y plus sigma w. If you have something more involved here, the multiplicative noise case, then you can also in some particular case, mainly in the so-called commutative noise case, you can also establish the Sussman transformation, but this is more problematic because then this form of this new function f and of the vector field for the random ODE is a solution of another ODE, so much more complicated. But nevertheless, this is a nice starting point in our opinion, okay? Because, as I've told you, the main issue with SDEs and to develop this loss function that we would like to minimize is having this Ito or general stochastic integral. We don't know the direct procedure how to define loss function that is acting directly on the SDE, not on some transform SDE to the random ODE or something more involved, but the one idea that please remember is to get rid of directly having the stochastic integral in the differential equation. Okay, so next question is what we would like to approximate if we are aiming to use neural networks, and as I told you, neural networks are the deterministic objects. So what we would like to approximate? Where is this deterministic part? And the answer is like this. We are using the so-called the universal representation theorem for solution of SDEs. This is not only one theorem about this, but I think we have proven the most general one that you can use also for SDEs driven by semi-martingales, the semi-martingales SDEs. Yes, maybe we'll also go for this direction with respect to spins, we'll see. But in this case, also it goes from this theorem, but also from some older one that you can you can express your solution Y, also X. Yes, but after this transformation, we are aiming at solving by neural network of the solution Y, and then transform back to the X. And nevertheless, if it's X or Y, you have this general representation theorem, but yes, because we will be approximating Y and then transform back to X, we are using this theorem for the Y process. And this theorem gets you the information that there is a Borel measurable function. In this particular case, this is this function psi between the space of continuous functions to the space of continuous functions is even Lipschitz continuous. I will not give you all the details are in the version 2 preprint, but it's even Lipschitz continuous. In general case, we don't know. When we have the semi-martingales, when we have Levy process, we know only that this psi between the Skorohod space and Skorohod space is only Skorohod measurable, we don't know any more regularity. In the Wiener case, we have more regularity, of course. which we also can use for the better approximating and so on. So the main idea is that since Y is a composition of deterministic operator function, and stochastic process W, we interpret this Wiener process here, the stochastic process W, as a random element, random variables with values in the Banach space of continuous functions. Okay, so we are using this functional analysis approach. So this will be the operator, so mapping between function spaces, and also we are using this representation of the Wiener process as a random element in the with the values in the Banach space. This is very important here to have it. And mainly where's the deterministic part now? It's very visible. It's just this is the deterministic part that we would like to approximate by using neural networks, this psi. And if you know some deep on it, yes, probably, I'm pretty sure that you know. This is, yes, exactly, this is in this direction. So we are looking about theorems that says that there exists neural network that approximates operators. Okay, so universal approximation theory, not only for the real functions from R to R or RD to Rn, whatever, but for the operators. Okay, from the operators between Banach spaces. And there are some results. Some of them I'm giving here, and mainly when you are using these theorems in the context of SDEs, they are for the Wiener part. That's one of the problems, theoretical problems. I asked the authors of this preprint about this general case when we have Levy process and when psi is a mapping between Skorohod and Skorohod. They don't know such a general theorems. Maybe they will develop it. I hope they will also give us note about this. But the question is very general. Is it possible by neural network to approximate operators? And the answer is yes, at least in the case of Wiener process. So at least in the case of Wiener process, we know that we have object that there exists object that we would like to approximate, okay? Because there exists this ideal neural network. We don't have, of course, access to this. It's general drawback of this universal approximation theorems, the only existence. But yes, still these theorems are very nice because they says you something deeper, that there exists we can say ideal neural networks. It doesn't have to be deep even, these theorems. It can be shallow, yes, with small number of layers. But in practice, they are deep networks, okay? So when we are now go to the minimization problem, we are looking for the neural network that will approximate this ideal neural network that sometimes we know that exists from the universal approximation theorem, yes? And this neural network approximates this phi. So yes, but for now we are skipping this UIT, okay? Because yes, this UIT is just for the existence, and we would like to give you answer how to construct the implementable neural network that will approximate this psi, and at the output we'll have the approximation of Y and X. Okay, so some settlements of the project in some space. So we are using the following space of adapted process that have almost continuous trajectories, and derivative of these processes are adapted again and Cadillac. And we are using the following norm. So with respect to the Y, with respect to the values, we are using like average supremum, and with respect to the derivative, you are using the L2 norm. So mixed supremum L2 norm. Also in the Wiener case, you can narrow this linear space, but we kept it also because this is very convenient when you are looking on the general Levy processes. And the theoretical loss function, because we are start with the theoretical loss, which is not implementable, and then we are heading to the empirical loss. So what kind of theoretical loss function you should define? In our opinion, this is the very natural extension of the one from the pin case for the ODs, okay? So because remember, we are now the aim is to define loss function for which the minimizer will be solution of the random ODE, not SDE, okay? For the SDE, even in the additive noise case, we don't know this direct loss function. So after transformation, we are looking the loss functions, which minimizer will be the solution of the random ODE. So you have here the extension, yeah? For the pins, ordinary pins, you don't have this guy. So yes, you have to incorporate it. So we do it directly. And also we are using this form that this is the expectation. You very well know because we are then heading to this Robinson-Monroe approximation and so on. And this tau is, you can say, random collocation point. Okay, this is a random collocation point. And now the properties, yeah? Properties are like this. Under the assumptions, the Lipschitz assumptions, you have like this. The first one, you have alternative, you can say, sometimes more convenient representation of this theoretical bar L loss function. And then you have, this is the most important from this proposition one. Having 0 for the loss function, this is the same like the 0 is also the infimum of this loss function over the whole this D1 linear space of this stochastic processes which I showed you. And this is, so minimization problem is equivalent to solving of this random ODE, as you can see here, okay? So for all processes from the D1, if you are achieving infimum 0, then Y is solving the random ODE, okay? And so the next question is about the existence of the minimizer. This is connected to the existence of solution, so the answer will be positive, you will see. But next properties, but in meantime, some more properties of L, okay? Again, under the Lipschitz continuous assumptions, you have the very nice properties, you know, that you would like to have when you are looking at the minimization problem from the optimization theory. We have consistency, okay? The big Y is the true solution of this random ODE, okay? So coming back here, big Y is the solution of this random ODE that we would like to solve, okay? That we would like to approximate. So we have the consistency. We have the consistency of this theoretical loss function. We have coercivity. So L also is tending to infinity when the norm going to infinity. So by using some infinite dimensional optimization theory, you can have alternative proof that you have a solution of the random ODE. So from the opposite, yeah, you are not from random ODE to the minimization problem. You can establish the existence of minimizer, but you can go from the opposite, yes, because you have coercivity, sorry. And also you have Lipschitz continuity. You have also Lipschitz continuity of the square of the loss function. So very smooth problem, very smooth problem. And also, this is rather direct corollary of the results and some theory from the SDE and random ODE, that under the Lipschitz assumptions, you have unique solution of this random ODE, and the unique solution, this unique solution is the global minimizer of this theoretical loss in this space of this stochastic process that we are considering. And so you have one global minimizer, unique global minimizer. But this is interesting that in general, this nonlinear function is not convex. Even if sigma is 0, of course, when sigma is 0, you are re-establishing the ordinary pins for ODEs. And also in the pin problem for ODE, you can check this in our preprint, the very, you can say, very direct counterexample that L bar, theoretical bar, is not convex. So you can have, yes, unique global minimizer without convexity. The convexity is only in particular case, when you have linear ODE, linear SDE. A is linear, okay? More or less. That I think, I'm not 100% sure, but you can even establish the equivalence of the convexity and having linear drift. Not direct proof I don't have now, but some estimate inside. Maybe there's even some theorems in literature. I cannot give you direct references, but the intuition is like this. Convexity in very particular case. For the nonlinear drift, that we like to solve, of course, many times, mostly. This is not the convex problem. And so,
Professor, I had a quick question.
Yeah.
Could you go to the previous slide, like slide 13?
13, yeah. Mm-hmm.
Yeah, 13, right. So capital Y is defined as capital X minus sigma times the Wiener function, right? And
capital Y, yeah.
Yeah, capital Y. Yeah. So, like, could you explain what do we mean by unique solution? Because Wiener process itself is introducing like a randomness into the variable, right? Like, what do we understand by uniqueness of Y?
From the unique solution, I mean the unique solution like the theory of stochastic differential equation. There is only one process, and if you have two processes, yes, each of them can have infinitely many trajectories. That's true. But by uniqueness, I mean something like this. If you have two processes, then these two processes has almost all trajectories the same. But the number, that's true, is infinite many. But this is not the problem.
Okay.
This is that if you settle small omega, you have infinite many omega, infinite many trajectories. That's true. But the solution is not one particular trajectory. Remember that. The solution of the SDE is not one particular trajectory. The solution of SDE or random ODE is stochastic process. And exactly by uniqueness, I mean I cannot distinguish between two stochastic processes. Okay? That's solving. This is, if I can only, because I don't have time here. Please take a look into the foundation of a stochastic differential equation and the definition of unique of solution. It is more or less like this. If you have, if you have two solutions, the uniqueness means that both processes has almost all trajectories the same. Which number for both is in infinitely many trajectories, possible trajectories, exactly. And that's why this is very problematic, exactly.
Okay, got it, thank you.
No problem. Okay, so going further, so now how to implement, how to implement is how to go from the theoretical loss function to the empirical loss function that we can run on the computer. The initial problem is infinite dimensional, So we are approximated this infinite dimensional optimization problem by finite dimensional optimization problem, or RN, of the Euclidean space, when now Ln, the empirical loss function, is again expectation, of course, but of this function, When you compare this empirical loss function to the theoretical loss function, you can see that you are switching from the process Y to the neural network, for which the input will be trajectory or approximation of trajectory of the driving process, In general, here in the ordinary pins, your input, for example, for ODEs can be very, very, very small, only the time point. For the time point. W are weights. Weights are not the input. So the input is the time point, for the neural network, and the approximation of the trajectory of the driven Wiener process. Of course, it has to be finite. So this is something like how to obtain this approximation. For example, by the incremental method, having sampled on some. You have to sample W, the Wiener process, on the finite mesh grid, But again, you have more input. How many more? It depends on the density of the mesh on which you are approximating the driven Wiener process. And this problem is at any approaches you can see when you are dealing with approximation of SDEs by some natural methods, Euler-Maruyama, and classical approach, or you are using some neural networks. Always you have to somehow sample the driving noise. So the input of the neural network will be the time point, and the approximation of the trajectory of the Wiener process. And then you will minimize it over the weights W. W are the weights of the neural network. There is another issue. No, not only one, okay? Here is the derivative with respect to time. So you need to use this gradient tape, whatever. Martin will say something more about this, to differentiate the neural network. So the neural network should be sufficiently regular, that's one. But here, I will go back, you have W sampled at random collocation point. This collocation point is uniformly distributed, and it's extremely important. It should be, it have to be independent of the driving Wiener process or driving Levy process, whatever you have there. So how to get the value of process sampled randomly on some independent time point, collocation time point. It's not direct. It's another approximation level. Here, because we have also in paper, we have two approaches. One is by so-called Levy bridges, okay? But Levy bridges are not always you have Levy bridges. The conditional law of the driving Wiener process when you have fixed Wiener process on the other time points, okay? That's the Wiener bridge, Brownian bridge. In the case of Wiener, you have the exact form of the distribution of the W conditioned on this vector, okay? The conditional distributions. That are the Levy bridges. In general, you don't know this, okay? So the second approach that we would like to investigate, that we approximate this in other ways. Some, for example, step functions, step processes, and so on. But this gives you another level of approximation, okay? More, you have here, as you can see, more level of approximation than you have in deterministic pins, because you have this, in this approach, you have this, how to sample this. You can sample this accurately only when you have the exact conditional law of the Levy bridge. And in the Wiener case, you have it. And so we can use it. But this is not direct. This is not obvious how to, obtain Levy bridges in, for example, in the case when you have infinite Levy measure. It's not, this is not known in general. You have to pick some special attention to particular Levy process then. Okay, so since empirical or theoretical loss function is the expectation of some function, okay, you can use now the stochastic approximation algorithm, okay? This is the classical one, the Robbins-Monroe, okay? The Robbins-Monroe. So the Robbins-Monroe more or less is like this. If you are minimizing function, which is defined by the expected value of some other function sampled on some random elements, then this Robbins-Monroe stochastic approximation looks like this. You don't have expectation here. You are computing gradient with respect to weights of this Hn function, which is given by 11. This is the classical one. And the SGD algorithm is a particular case of the Robbins-Monroe algorithm. So we can use SGD, but in program, Martin, we said something more, we are using some other approximation scheme. It's also doable. Okay, and so because I don't have, I think, yes, Martin time. So after minimizing, we are obtaining WV, okay? And then how we are defining the approximation of X on given trajectory of W. You are using this trajectory of W, okay? And then for the trained neural network, you are picking the time point as the input, and you are picking the approximation trajectory of the Wiener process. And then you have approximation of X that is corresponding to this trajectory of the Wiener process. That's the we can say whole story, okay? And I don't have much time here, so I will finish on this another theorem now. We can say the main theorem for now. The SIA type error estimate. You know the SIA type error estimate from the mass from the PD for the PDEs, partial differential equations. Okay, how to estimate the finite element method, the error of finite element method. And this is in this this lemma is in this fashion, in this spirit. The first one remark is that empirical loss is equal exactly to the theoretical loss in the Wiener case. So when you are defining the Y and W, the stochastic process as a neural network which is acting on the trajectory of the driving Wiener process. So you are defining this process like this. Here is the neural network, feed-forward architecture. Then you have this nice equivalence. This is because of this exact form of the conditional distribution for the Wiener case for the Brownian bridges. This is not true in general, okay? But this for this case, that's why the Wiener case is so important. You have this nice coincidence. And then you have this theorem. Under Lipschitz condition, from this, we have to assume you are picking the neural network for which this process is sufficiently regular, okay? So if you ask me, the neural network should be sufficiently regular, okay? Then you can apply this theorem. Then there exists gamma, the constant, such that for all W star, you have the following estimates. So this is the error, okay, for the peaked weights here for the neural network. The error in this one norm between the output of the neural network and this true solution of the random ODE is upper bounded, yes, by gamma times. Here you have the error, how far you are from the optimal one, okay? This is the infimum of this empirical loss. And you are picking now, for now, the arbitrary YW, so you're asking how far you are from the infimum. If you are far or not, yeah, if you are far, you have some additional error. That's true. And this is the minimal possible error. As I told you, this is in the SIA type fashion. This is the minimal possible error that you can obtain by using this, we can say, architecture of neural network, this kind of approximation for the true solution Y, okay? And if W star is truly minimizing this empirical loss, then this solution is up to constant, the optimal one. The optimality is understood in the same way like this optimality for this error estimate in the finite element method for the PDs, okay? So you cannot go better when you are assuming this form of neural network, okay? Of course, the question is, what if you take something else? For now, we don't know, okay? So from my side, that will be all. This is some special case for ODs, but now, yes, if you would like to, if you are interested, I hope for the more details, we have some in preprint, and now I'm giving voice to Marcin. Please present the numerical part. Maybe you share your screen, okay? Then.
Yes. I'm going to share my screen.
Thank you.
Probably Paweł. Oh, okay. Yes, you stopped. Can you see my screen?
Yep, I'm on slide 19, empirical loss function.
Yes,
the recap slide.
Exactly. Yep. Exactly. So before we go dive deeper into the implementation details, we need to go through quick recap about the empirical loss function. So our loss function contains two terms. First term is checking initial conditions if the network at time 0 is equal to the x0, and the second checking if the network satisfied random ODE. So for instance, we'll search for such neural network will satisfy two conditions. The first is the network shall satisfy the initial conditions. So the network at time 0 has to be equal x0. And the second, the network derivative with respect to the time for time 0 has to be equal this value, f at 0 x0 and w at 0. So we can force our network to return such value for t equal to 0, and this speed up the training process. How to do that? We represent model architecture. If you take a look at the first two rows in the architecture is a very basic feed-forward neural network. We have input layer. We take as input time and discretization version of the Levy process trajectory. Some dense layer. We choose then hard silo as activation function. I will provide the motivation for such choice later in the talk. And finally, we have output layer. And let's denote the output by bar n. And this is the most classic architecture. But to force our network satisfies those conditions which I mentioned before, we add additional layer. It's a simple transformation. Our network will return x0 plus time multiply the expected value of the derivative at time 0 plus t square over 2 and the output of the bar n. And if we put 0 by time, that second and third term will vanish, remains only x0, which will give us the first condition. And if we calculate the derivative of the network with respect to the time, the first term is vanished, remains only the value of the time of the derivative with respect to the time at 0 plus something multiplied by t. So obviously for t equal to 0, the rest will vanish as well. Using these transformations, we consider only neural networks will satisfy those. Will satisfy those two conditions. Now let's talk about the activation function and recap. Our f in the random ODE is defined as drift coefficients with small transformation. But generally, if you model something, we'll use well-behaved function. It's our best natural choice. So we can assume that if we assume the drift coefficients is well-behaved, and we'll evaluate the function f along a linear trajectory, the result will be non-differentiable, probably. So as the consequently, we'll search for network satisfy this condition. So the network shall have first derivative, but don't have the second derivative. And to obtain such network, we try use very widely behaved functions because ReLU is quite well behaved. Tangent is as well well behaved function, and hard-silo is the most widely activation function, which is accessible in the basic TensorFlow library. So this is our motivation for choosing hard-silo as the activation function. Okay. And okay, we are ready to talk about training process. So training process is very intuitive. We generate randomly a few Levy process trajectory, perform weights optimizations, and checking the results. But we observed that the networks appears to be over-influenced by the trajectories. There is a lot of noise, and the result was this network struggles to solve the case where the trajectory is equal to 0, the classic ODE. It's not okay for us. And to try solve this problem, we decided to add some trivial trajectories during the training process. And finally, first we train with randomly generated trajectories, perform Waze optimizations, and then train with trivial trajectories. We replace the trajectories value with 0 and then perform Waze optimizations. Using such approach, we will encourage the network to well approximate at least the ordinary differential equation. At least for the case the sigma is equal to 0. And this makes the result much better. And I think we can present some results. Here we can see some trajectories. The green line is exact solutions. We choose Ornstein-Uhlenbeck process. And the blue line is prediction of the neural network with the transformation, because we need to add sigma multiplied by the Levy process. For me, it looks quite good for a stochastic means. And additionally, we performed some numerical experiment for other Levy processes. And on the left side, we can see results for Ornstein-Uhlenbeck process, but driven by the Poisson process. And on the right side, it's as well Ornstein-Uhlenbeck process driven by the sum Poisson process and Wiener process. And that's all from our side. Thank you for your attention.
Thank you very much, Martin and Professor Paweł. Do we have any questions for the speakers?
I had two questions. So could you go back to the slide 21 or 22? I think where you were like mentioning about why you were using hard silu as the activation function. I think 22 maybe. Yeah. So I think so the motivation here is that you want to have the network such that it is differentiable once in time but not twice, right? Because Wiener process is not differentiable, right? So like how does hard silu help you to ensure that?
Because the hard silu is not it's more piecewise function. It's not a simple real function where you have only one point where the function is not differentiable.
Okay, so you're okay if you're having like piecewise break, like, because I think hard silu you define it like for different regions, like -3 and -3 to 3 and more than 3, right? Or something like that. So are you okay with having non-differentiability at the at like only discrete points where you're having those piecewise functions connected?
We searched for another. To be honest, I tried some very wild function, some kind of Weierstrass functions. But for computational reasons, the ready implementations are much more perform much faster than my custom implementation activation functions.
Okay,
And
I see.
That's the reason why I choose hard silu. It's the most widely function which I can find in the TensorFlow library.
Okay, makes sense. And also in the results that you were showing, right? I think slide 23 or 24.
23, 24.
Oh, yeah, this one. So I think like at several places there is some kind of a mean shift that we see in the results, right? Like even though you're able, the model is able to capture the profile very similarly, there is some kind of a mean shift that is happening in these results. Like any reason why you see that kind of a thing? It's not like the prediction is completely off, but it's more like capturing the profile but not capturing the mean.
We have no idea.
Okay.
Yeah,
But
there are lots of sometimes very strange phenomena, like in neural networks, and many of them are still you can solve by experiments probably, because we don't know theoretically why this shifts exactly. Probably it's due to this activations function, because as Marcin said, you would like to have non-differentiability, non-second differentiability anywhere. But it's very hard to obtain this, but that's the theoretical nature of this random ODE. You don't have anywhere second derivative. How to have it in exactly in neural network, we don't know. Just to have lots of points when you don't have the second derivative. Maybe that's the reason, but truly we don't. For now, we don't know. We are improving this, do some refactor of the code. Also, the links for the code is in the this preprint on the GitHub. You can take the codes. If you find something better, please let us know. We'll be very grateful. There are some examples for the nonlinear SDEs, and we are now working for the experiments in more than one dimensional, 3, 2, 100, and so on. We'll see which experiment will show in the next version, but we have also some experiments for the higher dimensionals, and they're also we can say good, but still work in progress. Yeah. But if you can refactor the code, it will be great. Let us know.
Okay, thank you. I think it's a great work. Seems very rigorous and mathematically based. So yeah, thank you.
Thank you very much.
Thank you for the question, and I would like to thank Martin and Professor Paweł again for taking their time to present their work. And now let us move on to the next talk.
Thank you very much.
Thank you, Professor Paweł. Thank you, Martin. Professor Yeung, could you hear me?
Hello. Yes, I'm here.
Yeah. Could you please try sharing your screen?
Yes.
After you start sharing, I'll introduce you, I'll make the announcement, and then you could start presenting your work.
Are you seeing my screen now?
Yes, I can. Would it be possible to go to full screen?
Yes, I'm going to make it full screen.
Mine be in view. Yeah, full screen mode. The first option. Presentation. That's perfect. Yeah. And okay, let me just quickly introduce you, Professor. Yeah. So moving on, for the next talk, we have Professor P.K. Yeung from Georgia Tech, who will be presenting Exascale computing and multi-resolution independent simulations paradigm for intermittency in turbulence. Professor Yeung joined the aerospace engineering faculty at Georgia Tech in 1992 after postdoctoral appointment at the Penn State University. He has held the rank of professor since 2005 and has been a professor of mechanical engineering by courtesy joint appointment since 2010. He has held visiting appointments at the Chinese University of Hong Kong, Department of Physics, and Hong Kong University of Science and Technologies, Department of Mechanical and Aerospace Engineering. Professor Yeung is a world-class expert in direct numerical simulations of turbulent fluid flow, with particular interest in intermittency, mixing, and dispersion, and in the development of massively parallel computational algorithms, which have enabled simulations of the largest size known at the present time. His work has been supported by the National Science Foundation, the Environmental Protection Agency, the Department of Energy Oak Ridge National Laboratory, and several major national supercomputing centers. He has served on advisory bodies convened by NSF in the area of advanced cyber infrastructure. Professor Yeung served as the chair of local organizing committee for the 71st annual meeting of the Division of Fluid Dynamics of the American Physical Society. He has worked with American Association for the Advancement of Science in offering summer internships for undergraduate students with disabilities. With this brief introduction, I would like to invite Professor Yeung to give this talk, but I would like to make an announcement. If you have any questions for Professor Yeung, please chat it. Please write down your questions in the chat. That would be easier for Professor Yeung to answer the questions. And with that, I would like to invite Professor Yeung to present the work. Thank you.
Okay. So good afternoon, everyone. I'd like to thank the organizers for having me in this seminar series and a very nice and complete introduction. Also, they actually kindly accommodated my request to move the dates of the seminar from a certain time in the last month. So my work in the last few years has been a mix of turbulence as well as large-scale computing, and I'm happy to talk about both of them. On the other hand, well, on one hand, we like to do large simulation. On the other hand, we like to make sure that the simulations are useful. And that's what this multi-resolution independent simulation is about. I'm going to talk about this in more detail. I'd like to acknowledge support from the Department of Energy, Insight Allocation at Oak Ridge National Lab. And we also have support from NSF via a grant to Johns Hopkins University with Professor Charles Manifold as the PI. And so I'd like to thank again everyone for, especially at Brown University, for having me. And my students have you see some of the contributions as well. To say very briefly why turbulence is challenging, why this is important, why this is worth spending time on. Turbulence is an unsteady flow. Well, you have an unsteady and three-dimensional flow, and on top of that, we have disorderly fluctuation. We have a highly nonlinear nature, and we have stochastic character, and over a wide range of scales. So all this together makes turbulence very complex. At the same time, turbulence has many applications in nature and engineering, and we can see some of these graphics. Extreme weather in the form of flooding caused by a hurricane, apparently. We have an aircraft taking off. We have trading vortices. We have pollution problems, and also I think once in a while we will be the person in the picture as far as the last one is concerned. So we'd like to have fundamental understanding, given how complicated this phenomenon is. And sometimes our research is driven by both curiosity as well as practical needs. We'd like to see what are the important problems that we need to understand. And at the center of this is the idea of intermittency. Intermittency is essentially we have a localized activity. We have very strong activities. In, let's say, for example, if we have extreme rainfall sometimes can cause flooding. But they are localized and they do not last for very long periods of time either. And I'm going to introduce the direct numerical simulation, although I suppose many of you will be familiar with this. We would like to consider a relatively simple geometry. We'll say that there's no mean flow. And then we want to solve the equation for conservation of mass and conservation of momentum, given by the so-called Navier Stokes equations, where the nonlinear terms on the left-hand side, the pressure gradient, the viscous term, as well as any kinds of forcing mechanisms, both numerical or physical. And in order for the simulations to be accurate, we need to have a domain that is larger than the larger scales. And also we have a grid spacing that's comparable to the smaller scale, which is called the Kolmogorov-Lane scale. And so and the Kolmogorov-Lane scale is related to the viscosity and the energy dissipation rate. And so in each direction, we would have the number of grid points being the length of the domain divided by the grid spacing. And in turn, that's proportional to the size of the larger scales and the size of the smaller scales. And that we know that ratio increases strongly with the Reynolds number. So we want to simulate high Reynolds number turbulence. There will be some challenges. There's a well-known approach of essentially Fourier pseudo-spectral. It's all traced back by Rogato, 1981, and NASA Ames. And the idea is we start with wave numbers, essentially in wave number space. We would represent the velocity as a Fourier expansion, And we start with the wave Fourier coefficients in wave number space. We transform them to physical space. We form the nonlinear products. So we can rewrite this nonlinear term in a way that will be easier to compute. And then after we evaluate the nonlinear term, we do a transform back, and then we perform differentiation. And then we advance in time. We typically use a explicit one-scatter method. One of the advantages and the challenges itself of DNS is that we have a lot of detail. For simulation on periodic domain, you can find some public data available, in particular at the Johns Hopkins Turbulence database. For the growth of computing power, I look at a website top500.org and got this graph here. This graph shows that the computing power, let's say the logarithmic scale on the y-axis and linear on the x-axis. So a straight line means that we have essentially exponential behavior, exponential growth, and and we'll see that that there are different data points here. The ones in brown, these triangles represent the top computer in the world at any given time. And we are happy have been able to assess some of those machines. We have a massive parallelism. The solution domain is distributed over a large number of parallel processes. And that is necessary because of the memory requirements, but also they have some challenges as far as how scalable the code would be. Currently, as we know, GPUs are the dominant technology. Perhaps in 10 years that will become quantum, but for now, we're working on GPUs, and there are 3 exascale computers in the world. I think all of them were operated by the Department of Energy, and we have been using the first one, which is called Frontier, and we have to adapt from CPU to GPU. When we started, we have to make sure that data movements can be optimized as far as possible, because that's what takes the most time, rather than the computation. We also have an eye on the next generation machines now on the horizon in the next few years. So despite supercomputers or leadership class computers being very powerful, we not have to accept that the amount of computational power available is essentially finite. So how much can we compute? That is still the question. In the idealized scenario, if everything is perfectly scalable, the cost per grid point would be a constant. That is the ideal circumstance, not the ideal situation. But we also have to make sure that we satisfy numerical stability. So delta t will be proportional to delta x, and that would lead to another factor of n. So now the cost will go like n to the 4th. If we want to halve the grid spacing for better accuracy, better resolution, then the cost will increase by 16 times. Then this is a big number, because if we watch the trend for the supercomputer centers when they talk with great excitement, what about the next big machine coming? We find that the next big machine is more powerful with the current one by a factor of somewhere between 5 to 10, not 16. So if we can simulate bigger, but then our simulations will get smaller. We get shorter and shorter. And besides, there is a great demand for computational resources from the other disciplines. So there has to be some trade-off, perhaps. And so there are 2 options here. One, I call it temporarily like option A. We insist that we want to have a very small grid spacing. A small grid spacing can allow us to get high Reynolds number. But then, because the resources are finite, we won't be able to take over the computer for ourselves. And so we won't be able to simulate very long, and our time span would be measured in the order of several Kolmogorov timescales. The other thing is, well, if we have lower Reynolds number, or if we're happy to live with a modest resolution, then we can run in the traditional way. We can run several eddy transfer times, and that will give us very good time averages. And in a way, this is the contrast between the first approach. We would call it capability computing, as well as versus the second is essentially capacity computing. I find that supercomputing scientists generally prefer people to run so-called capability jobs, because they would like to say, well, our big computer is enabling simulation that cannot be done elsewhere at all. Right? So and the scheduler generally would give us better treatment, and as far as what about we want to run several eddy transfer times. I'm afraid our experience is that the jobs will be waiting almost forever in a long queue, spreading several months at least. So now the question, if I'm going to be favoring short simulation, one can ask, can they be useful? Just simulate something for several Kolmogorov timescales. Well, if the timescale of the phenomena of prime interest to us is in the dissipation range, then that's possibly okay. If you think about extreme events, in the case of a thunderstorm or essentially a bolt of lightning or something, how long do they last? So can we and also how large a land area that's being affected? We see that there are some extreme events that are localized but in both space and time. It's also our experience in search of a better resolution. We find a grid spacing. Then, of course, the high wave number n of the spectrum will start to change, and the change seems to be nearly complete in about 1 Kolmogorov time scale. We have to worry about sampling too. I'm sorry. So if we are able to average over a long period of time, that our sampling would be the best. That is possible, but that will be difficult if we say that we can only run several Kolmogorov time scales. So what we can do, I think, is we would take the approach of ensemble averaging. We start with several simulations. They all run for several Kolmogorov timescales, but they have statistically independent initial conditions. And they can be coming from lower resolutions as well. The other thing is that, or the fourth thing, this is not necessary to produce statistical seasonality. It's also relevant. I would say that there's no perfect forcing scheme. Every forcing scheme has its own properties. But we have chosen an approach which is better for our specific purposes. So then we proposed this approach MRIS in the paper 2020 in PRF. We start to observe we start with observation that long simulation we accept that a high Reynolds number, high resolution are not likely to be feasible. Or in other words, DNS is not going to be a perfect activity. But then we may be able to run a simulation at lower resolution for a longer time. So we start with this. We start with a long simulation at a modest size at a desired Reynolds number. And then we would take instantaneous snapshot. We'll take several of them. I said well separated, considering that they may be coming from a long simulation and with sufficient separation for us to obtain some degree of statistical independence. So with these modest size snapshots, we find the grid. We run for a couple of time scales. When we find that the small scale actually they do adjust very fast. We have some tests to validate the whole idea. Can we try to say, let's say take a well-developed DNS snapshot that we trust, and we will truncate the high wave number. And then that will make it become something like a low resolution simulation again. But now we can see how long does it take for it to recover the original state of the equilibrium. So as I said, we perform ensemble averaging over multiple realizations, And our idea is to try to limit the number of time steps, expensive time steps. There must be one at the highest resolution. And we find, and in the paper that I mentioned, there are some results that we can look at. But I will skip that for now and say, let's say when you think about fundamental turbulence, why do we want to run a large simulation? What are we going to learn from that? Some of the natural questions outside our field, for people outside our field, maybe say, if the fluctuations, are the fluctuations small or large? If the fluctuation is small, can we negate them? We find that that's not, depends. If you look at it at the small scale, the fluctuations can be very intense, can be increasing with the Reynolds number. Again, the question is, can we calculate or measure it, sample them properly, and understand the properties? And we'll be looking at fluctuations of velocity, vorticity, pressure, passive scalars, and gradients of everything. And how do the statistics vary with scale size, especially in space? There is a well-known Kolmogorov 1941 and subsequently 1962. And we would be looking at spectra, structure functions, local averages, and some of the scaling exponents as well. A very important question for DNS is, how does the turbulence scale with the Reynolds number? Let's say that we have if we use the largest computer that's available to simulate turbulence at a high Reynolds number, well, what about if we want a Reynolds number even higher than that? Then we will say, can we extrapolate? Whether we can do so is very often very problematic, but at least we need to have a good understanding of how the Reynolds number dependence actually is like. Okay, so seasonality and Reynolds number. So here we come back to talking a little bit more about the forcing isotropic turbulence. We would like to reach seasonality as soon as possible, but because we would like to save on the cost in computational resources. And if we can say, the idea we use here is that if we have reliable statistics on the energy spectrum at low wave numbers from previous work, let's say, can we let the turbulence evolve in such a way that that the energy spectrum at the lowest wave numbers are fixed at some of the average values? So that's what we have done in the paper Diego Donces and myself. And to obtain progressively higher Reynolds numbers, we'll start with some older data sets. We will freeze the spectrum as lowest field wave number shells, as I just mentioned above. Then we go to a finer grid. We would just then we get a lot of additional wave numbers which have zero Fourier coefficients to begin with. At the same time, we reduce the viscosity. We reduce the viscosity in order to target a new value of the Kolmogorov length scale. Essentially, we like to keep eta over delta x at a relatively stable value. Right? Because if we have a smaller delta x, we should be able to accommodate a smaller eta, and a smaller eta in general. In this case, with the forcing parameters fixed, would be coming from a reduced viscosity, and the Reynolds number that would naturally increase. So we can repeat the process to go to Reynolds number from Reynolds number 1 to Reynolds number 2, Reynolds number 3, and so on, and you eventually get the highest Reynolds number that we can that we can manage. At the same time, we also we also make sure that we respect the resolution requirements of a study in time and space. In the paper myself, Professor Srinivasan and Prof 8 years ago. So what happens when we try to increase the Reynolds number? So let's say some of these graphics. So the red line is for data starting at R lambda. Is for data that where we want to settle at R lambda 1,000. The blue line is for data where we want to settle at R lambda 2,500. And we start with this. And before this, we start with a lower resolution, lower Reynolds number. Sorry, we started with a lower Reynolds number, and we reduce the viscosity. We reduce the viscosity, the dissipation rate instantaneously would drop, and then the property of so-called distribution anomaly eventually would express itself And after a certain number of Kolmogorov timescale here, about 50 of the order 50, then it starts to come settle down on a relatively stable value. And the same thing for the our lambda. Our lambda was very large, artificially large, because we're reducing the viscosity. And our lambda divided by the initial value, you'll see that from these graphs, we can get an idea when is it that we might be comfortable in saying that now we have reached a new stationary state at the desired Reynolds number at the desired resolution. And we also, of course, we are going to we have done work where we find the grid spacing towards a higher resolution. We have a paper in JFM Rapids last September. This is a relatively short paper where you focus on essentially the small scale properties. And here I have extracted one of the graphs in that paper. We have grid resolutions 2K cube to 32K cube, and our lambda about, let's say, 400 to 2500 or essentially a factor of 6. And many of us would have read in some traditional turbulence textbooks what is the relationship between our L, the turbulence Reynolds number, relative versus our lambda. And there's a power law, and we in fact we have a pretty good handle on this. So we see the dotted line almost coincides with all the symbols that we have. And on the right hand side, we have the ratio between I think okay. The triangles represent the ratio of the length scale, and the circles represent the ratio of the time scale. And it's also well known that they increase with Reynolds numbers essentially at quite different rates. The so-called dissipative anomaly is that the normalized dissipation does not change with Reynolds numbers very much. We see the data seems to be consistent with what we know. There's some comments that I'd like to make about the Reynolds number before we move on to the next set of results. We can we were focused on studying laminar flows. Let's say we asked the question: at what Reynolds number does the flow become turbulent? Then we use so-called mean flow velocity, without the when you have a laminar flow, maybe we can do away with the word mean. And the large eddy length scale depend, let's say the diameter of a pipe or something. We have the Reynolds number, turbulence Reynolds number. Now we replace the mean velocity by the IMS velocity fluctuation, and they keep the large eddy length scale the same. Often then there is a discount of something like 20 times. Our L would be much smaller than our E. Our lambda is even smaller because we're using our lambda. And so our lambda 2500 actually is quite high. My estimate here is that it can be corresponding to. I'm sorry, this should be our E. There's a typo here. Our E about essentially 4 million. And what is the highest that can be gotten in laboratories? I'm not an experimentalist, but I know that there's a well-known facility, MPI, Max Planck Institute in Göttingen, Germany, and they're able to get our lambda 6,000. So I would argue, perhaps optimistically, we are not too far behind. So instead of talking about a low Reynolds number, hopefully we can avoid that label to some extent. And here is some results on the energy spectrum. How does energy spectrum change? Our lambda 650, this is the line in red, and there's 3 lines in gold which are all at the same Reynolds number, but at different resolution. And we can see that you can see graphically something close to k to the minus 5 or something like a power law. We should measure that, of course, on the right hand, and in the middle we plotted the compensated spectrum. We have the so-called bottleneck, the KE talk about 0.1 to 0.2, and we do see that there is some scaling, but the scaling law is a little different from Kolmogorov. So essentially the slope is steeper, I think, steeper than minus 5 thus. We also could look at the one-dimensional spectra. These are the longitudinal transverse, and up there, that is the 3D energy spectrum. We have checked that isotropy relations hold well, but then there is something that we still have to understand why this is the intermittency coefficient relatively large. And going to physical space statistics, this is inertial range. This graph is focused on the inertial range. Kolmogorov 1941 says that the third negative of the third order structure function divided by epsilon and r would be a constant. In fact, the so-called the Kamenhofer equation allows us to say that that constant should be 4 thus. Are we there? We are sort of close. I think. But one thing that is reassuring is that as the Reynolds number increases, you can see that the scaling apparent scaling range does become wider and wider systematically. What about high order structure functions, which are more related to which are more important when we talk about extreme events? Because extreme events, you would have with extreme events, you can have very large velocity increments. You have some large quantity raised to a higher power, then it becomes even bigger. So these dashed lines, there's some dotted lines here. Dotted lines here is a mesh. They represent the so-called ballistic or the dissipation regime, where S6 will be proportional to r to the power 6 divided by r squared would be r to the 4th. And then the inertial range of the at least 30 or 40 length scales, Kolmogorov length scale, we see some scaling, but also we find that the slope is not what classical Kolmogorov theory would be suggesting. And we take on the right hand side, we make a plot of the so-called logarithmic local slope. If Kolmogorov scaling was perfectly right, and it would be flat at p over 3. Well, this is. I'm sorry. It would be not just flat, but it would be 0 because of the way that this plot is made. So the data lines falling in the negative range means that there is significant impact from the idea of intermittency. So we find that the dissipation rates can be taking values which are very large. And the next is a graph that is sort of tentative, relatively rough. On lambda 650, we have order 2, order 3, 4, 5, 2, 4, 6, 8, 10, and 12. On lambda 2500, the same thing, from order 2 to order 12. And we can see that there is a significant increase in the curvature of something like a plateau at the high Reynolds number. The scaling is considerably better developed at high Reynolds number. If we have low Reynolds numbers, we can say what we need about lower order moments and high order moments. We will not have that kind of confidence. And now the scaling exponents. This is a plot. I'm sure many of us would have seen a plot of a similar kind in a book by Navier Stokes, 1995. The scaling exponent as a function of the order. K41 would be P over 3. That would be this dashed line. And they are I'm just trying to see if our simulations are capturing quantities essentially in the right ballpark. If we have a normal with a certain intermittency exponent that comes from how the mean square of the local average of energy dissipation rates varies. If you take different values, I think 0.225 is probably the most reliable value. And the data seems to be giving reasonable agreement with not normal, although I should add immediately that, of course, not normal, we now have a problem. We have a problem with P goes very high. If P goes very high, the exponent can be actually on the wrong side. There is also a theory, so-called not Poisson, this particular formula, which is black, and does not seem to be agreeing that well. And then another thing we're looking at is the differences in scaling properties between longitudinal increments and transverse increments. Longitudinal, this is both of these are outnamed 2,500. The left-hand side longitudinal, and the right-hand side is transverse. I have, but we have to pay. I want to point out about the scales here. You'll see that for transverse transverse structure function, they have exponents which are on the order twice as large, maybe. And also the scaling is not so well developed. So one can say that transverse increments they deviate from Kolmogorov 9041 more. Now, another thing about local averages, Kolmogorov 9062 gives a special importance to the average of epsilon over a sphere of radius r. In DNS, it's usually more convenient, at least, to average over a cube, which is of length r on each side. But in experiments, often we have three-dimensional averages may not be applicable if the flow is not homogeneous, and in particular, also measuring 9 components, du, I, dxj, to form the complete signal for epsilon. That's very difficult. As a result, there has been in the history of the subject for some time, there is a lot of use of the so-called one-dimensional surrogate. 15 times mu times the square of du dx. Why is it like that? Because if local isotropy says that the mean value of this epsilon 1 will be the same as the true epsilon, but same mean value does not mean the same PDF, and in fact epsilon 1 is systematically more intermittent than epsilon. So there's some disconnect between the three-dimensional epsilon in theory and DNS and the one-dimensional version in laboratory data. I would like to understand, see if we can address this question more rigorously. And recently, my friend Professor Goto from Nagoya in Japan, we have a paper that's under review at JFM now. We're able to obtain an exact transformation relation between the PDF epsilon and epsilon 1. And the main trick is that we're integrating in multi-variable sample space. Take the joint PDF, you integrate over some of the variables. And the main assumption is isotropy, but there's no dependence on the Reynolds number. And we have some results here. I'll name the 2500 on the left hand side. We have you'll see that there are actually 4 lines here. They are very close. You may see something like red and blue coinciding, and there is green and black almost coinciding. So they're coinciding. They're almost coincident. That would say that we have very good agreement between the DNS as well as the transformation relations that we have used. At the same time, we are able to also see that there's systematic differences between the two signals, the 1D and the 3D, in the limit of small fluctuation, large fluctuations. One of them is more intermittent than the other. On the right hand side is a plot of the moments. Moments of epsilon 1 divided by moments of epsilon. This is order n, and we have data. We have data as essentially as 3 different Reynolds numbers, and we find that the agreements are actually very close. So that gives us some confidence that our fit is reasonable. And now going to computing, we have a paper focused on GPUs. In the Journal of Computer Physics and Communications, and this was published in January. In January last year. So the just for some background here, the cost of our pseudo-spectral DNS is very closely related to the cost of performing three-dimensional FFTs. For three-dimensional FFTs, we have to do Fourier transforms in all three different directions, and we talk about domain decomposition. We have to divide the data into different portions, so that each portion would be handled by different MPI or on a parallel process. And we use a two-dimensional decomposition in order to be flexible. We can say how many rows and how many columns. So the illustration here is 2 rows and 2 columns. And this allows us to use the number of MPI tasks greater than n, where n is the number of grid points in each direction. Well, basically, we do an FFT in X, so when the FFT, the data and all the data are locally available in X direction, and then we have to do a transpose to another direction. I think the labeling of the graph is a little inconsistent with my text. But in the text that we have actually X, C, and Y. X, C, and Y, or X, Y, C, this is just a matter of preference actually. Which axis do we want to call that? We have a row communicator here, and we have column communicator, which is the one that is more time consuming. So what is our so-called programming model? What is our programming approach? In other words, we want to get the best performance on frontier, and in particular also we want to be able to simulate the largest problem size that the memory on frontier can actually provide. And frontier has the special characteristics that unlike earlier generations of GPU machine. The GPU, or the so-called device, has the same amount of memory as the CPU. Right? Because I mentioned that, because 10 years ago, the GPU machines were well known already for very fast compared to for the CPU, but they had very small memory. And so basically whatever memory now for frontier, if the CPU can accommodate an n-cube problem, the GPU can accommodate the same n-cube problem. So we don't have to transfer data back and forth between the host and the device. We try to very aggressively avoid that. We let the CPU be idle. Are we putting something to waste? Not so much, because the GPU can be easily 100 times faster than the CPU. So all of the operations are done on the GPU. What is the CPU memory being used for? Occasionally, it can be used as a backing store for some compute-intensive quantities that we have computed, and we don't want to recompute. We'll pay the price for copying between the host and the device. We usually do that. We make use of that in post-processing codes where we are less concerned about what is the work time per step. We're using OpenMP 5 plus offload to GPU. There's a huge parallel region defined in the main program, and inside that parallel region, everything happens on the GPU, except for some I/O. If we want to check some numbers, work it out. What is this? What is that number? But we have to be very careful about minimizing the memory footprint. For example, if you think about all-to-all transposers, can we make there will be some intermediate buffers, the send buffers and the receive buffers, and we try to use the device pointers to allow different arrays to occupy the same space. And we do monitor the actual GPU memory, and we have a formula that is accurate to within about 2%. And we may, of course, have to change our strategy for machines in the future, but OpenMP should be around for quite a while. And this is just a very quick look at the coding. The MPI all-to-all, this is relatively well known. We have a send buffer. You have the message size, what is the type of the data, and the receiving buffer. and the name of the communicator, and so forth. So these two blocks of code, GPU MPI equal to 0 or not equal to 0, actually differs. Not so. Actually, the difference is very small. I think NBLK here we can consider that to be one, and the difference is that if we since we are doing all the computing on the GPU, if we do MPI on the CPU, we would have to pay the price for some extra copying before the MPI and after the MPI. We are mainly going to do GPUs, use CPUs to do the MPI. So we use this device pointer to make sure that the MPI, the so-called GPU-aware MPI, will understand the data, understand that the data is already on the GPU. And then the other thing about computing, we have the so-called OMP target. The word target means the operation will take place on the device. Teams distribute parallel. This allows the GPU to manage its own business. Each GPU that we are told that have been told that a GPU on Frontier can have thousands of threads. The thousands of threads will give us so many units of work given by the scope of these four do statements. These collapse 4 within this space, this parameter space. The GPU would essentially manage the work themselves to make sure that there's no conflict, and then make sure that we can get correct answers. So nevertheless, how well does this code scale? There's more details in the paper, but I will show here graphs which shows the elapsed raw time per time step versus the number of nodes. And on each node, we have eight GPUs, by the way. We have problem sizes n in each direction, 2k, 4, 8, 16, 32. And you see that there are a number of dashed lines as well as dotted lines here. If the data falls on those lines, then the scalability is 100%. If we go, let's say 8k cube, we multiply. We have used 8 times as many nodes. You see that we get the Schwann scaling is nearly perfect. With scaling is also very close. There are 2 exceptions. The 2k cube was scales poorly compared to 4k cube. That's because actually 2k cube scales extremely well compared to 4k cube. But 4k cube relative to 2k cube is not so great. That's it. But that's the artifact of the say 2k cube can be run on just one node. So any communication is extremely fast. 4k cube now we see now we have 8 nodes and then and so on. And on 32k cube now we have actually we push everything to the extreme limits, then the scalability does fall. It's not so surprising given the design of the machine actually. So now I'll talk about the Lagrangian point of view also because this can help us understand quantify some important issues. How does the turbulent transport material entities or fluid properties in space? And in particular, if the material properties is a cloud of something, at the same time that the cloud is spread out, there's also the chance that there could be some local build-up of something. And direct numerical simulations is a very powerful source of data for this type of modeling, essentially stochastic modeling. And we have implemented particle tracking. As you know, Eulerian code, the communication is the main thing as far as the cost is concerned. We can handle more than 1 billion particles in the larger cases, and we also do interpolations for velocity gradient and the pressure. Acceleration can also be computed from the Navier Stokes equation. But let me go to go to some of the equations. In addition to fluid particles that follow the fluid faithfully, in principle, we are also interested in what happens with small particles, which may have some inertia whose density may not be exactly the same as the fluid. I think This happens in experiments. In experiments, we need seed particles. We like to the seed particles to exactly follow the fluid. One could ask, there's some discrepancies that might develop over time. So this is the equation of motion. This is the rate of change of the velocity of the inertial particle, or in other words, the acceleration of the inertial particle, equal to a certain factor that is sensitive to the density ratios times the acceleration of the fluid. And then there is another term that is sensitive to the velocity differences. And tau p essentially is the particle response time, has something to do with the size of the particle as well. And we can look at this equation as a first order ODE. As the first order ODE, if we are able to compute everything about U, including its material derivative, and also the last term here, then we're going to denote the material derivative as the acceleration. So we have a formula like this, where happily all C1, C2, and C3, they are all simple functions of delta t divided by the particle time scale. And there is some burden in calculating acceleration. Acceleration has to be obtained by from the pressure gradient, and the pressure gradient is satisfied, and the pressure comes from the Poisson equation, which is a nonlinear right-hand side, so it requires some care in getting removing the aliasing errors. And here is a table showing the contributions to the total time from the Eulerian operations, generating Kubrick-Spline coefficients, forming ghost layers, forming ghost layers. I should back up a little bit. So we have n Kubrick points, and we give you n plus 3 Kubrick-Spline coefficient. And why do we need ghost layers? Because the particles may be going in and out of a certain subdomain, and we like to minimize the number, minimize the communication. So we let each MPI process have access to some information from its neighbors, and that is done using one-sided communication. And actual interpolation summing over 64 numbers. Actually, that does not cost so much. Acceleration field, yes, that is substantial. And without the a year and a half ago, my student Rohini presented a poster, Supercomputing 24, which had the data, has much of the data here, except we had not implemented inertial particles with the acceleration term yet. Yeah. So and also I should note that the design of an algorithm is that the only contribution that really depend on the number of particles are the two which look almost trivial. So we can multiply the number of particles by a factor of 10, and we can talk about the same cost. There's one coefficient, though. Actually, we have a tridiagonal system, periodic boundary conditions, and we have made some relatively recent improvements. And I know that the time is getting short now. Now, next is just very quickly about visualization of massive data sets. 32K cube is 35 trillion grid points. How do we look at all of that? We have to be selective, obviously. Which parts of this, which regions that have some properties that might actually attract our interest. And here with the example is what about the pressure fluctuation? What about the vorticity fluctuation? Vorticity fluctuations, I think the ideas of worms and so on may be well known. As for the pressure, we do know that low pressure seems to be associated with rigorous motion and motion of high vorticity, and we're trying to understand this on the right. And this is all from a 2500 outnumber 2500 32K cube. We have chosen on the left-hand side a one subdomain that has a relatively high vorticity, relatively high entropy. The square of the vorticity actually starts from this. Okay, and then two of these immediate neighbors, and we're looking at the pressure, and we are using volumetric rendering with an opacity map, so that we can get a better idea of what goes, get a better three-dimensional feel. Basically, here the brightest region is the region where the pressure is the lowest. And we will see. Okay, I probably yes. So I want to go back and say. So on this page now, everything is essentially coming from the raw signals. Right. So we can see that vorticity is very localized. And now if we're going to filter the signal, if we're going to remove everything that is smaller than the Taylor length scale, which turns out to be about 90 grid spacing, we see that suddenly there is some clear resemblance between the pressure, the low pressure, and the high vorticity. So that we have been working on trying to obtain some quantitative statistics to go together with this. Then what else is going on? We have Lagrangian studies of intermittency. We have passive scalars at modest Schmidt numbers as well as high Schmidt numbers. High Schmidt numbers requires a different code. High Schmidt number is a case of low diffusivity is very important, essentially for the ocean, where the Schmidt number is something like 700. And we're happy to share the data with the community. We have done that publicly via the Johns Hopkins Turbulence database, and where we have one snapshot, the UVW as well as the pressure that's in physical space. This may or may not be adequate for different purposes. So we are happy to work with other researchers if they like to assess our data to a greater degree of detail. So the final comments say in turbulence, I'll say that we are never satisfied. 32K cube is the largest in the world. I think it may be, but then we don't want to stop there. At the same time, we want into competition with other fields of science. And the turbulence, the problem we have to, I think we will accept that this is a difficult one. Do we want to have sudden transformative advances? That would be nice, but things may not naturally happen that way. As far as computing, we have to be able to adapt to the computers, including the current one, in any that will be coming as part of the next generation. And sometimes we find that advances in resolution may also challenge established knowledge. Sometimes we find certain things which are new, or that we find things that we were not confident of before, and also so I think that is a great motivation. There's still a great case that can be made for doing simulations that are larger and longer, better sample, and all of that. And we would like to be able to follow the dynamics of the structure. Intermittency, for example, is mostly in the form now studied in terms of spatial properties. What about the dynamical picture when those things have changed? And we like to play a role in the move towards more AI. At least we are associated with the Johns Hopkins Urban Database, which is one of the 10 datasets selected by NSF for purposes like that. Okay, thanks everybody. I hope to be able to answer some questions.
Thank you, Professor Yeung. It was a very interesting talk. Now we can ask more questions to the speaker. We already have a question in the chat.
Is there one? Oh, there are 5. Okay. The first question: do these simulations use adaptive grid refinement? No, it doesn't. We would refine the grid at some point, but it's not adaptive. And I think it might be nice to make it work, but to be honest, I need some ideas for that because in turbulence, the extreme events are very spotty. So where do we want to refine the grid, and also perhaps pseudo-spectral methods would not be suitable for that. I think because pseudo-spectral Fourier transforms, the grid spacing is not part of the formula. We assume that all the data points are equally spaced. And the second question, as we go to higher order lambda, do we find a continuation of the same scaling trends, or is there something new? That's a very important question, obviously. I think we do find we do have some evidence of phenomena that are not clear before. For example, if I go back to one of these slides, and I'm talking about Reynolds numbers for now, but also there's a similar point to be made about resolution. Okay, so this graph is outnamed the 650 and 2500. Although both graphs are sort of rough, I say this should be improved to some extent. We can see that if we are going to look at outnamed the 650, we may not know that the transverse spectra have the transverse structure functions have their own scaling too. Although the exponent is different from the case of a longitudinal. See. Maybe I'm okay. So basically, we would not be we not be able to get the same kind of scaling behavior. We also see as far as resolution goes, we know that if the resolution is not adequate, some of the extreme events would go unnoticed. At the same, although one other thing that we will find, I found in the paper in PLF 2018 is that if the resolution in time is not good enough, then actually we could artificially, we could somewhat surprisingly end up with dissipation fluctuations which are larger than they really are. We also, I think in terms of machine learning, also I'm by no means an expert in that area, but I was saying that we need the data high Reynolds number in order to be able to extrapolate with some more confidence about what's going to happen at some high Reynolds number, let's say 10 times of 2500, that won't be reachable for a number of years. I hope that helps.
Yep. All right. If you don't have any further questions for Professor P.K. Yeung, I'd like to thank the speaker again, all the three speakers, Professor Paweł, Martin, and Professor P.K. Yeung, for taking their time to present their work at Crunch Seminar. And with that, I would like to close this week's Crunch Seminar and hope all of you have a great weekend ahead. Thank you.
Okay, thank you very much.
Thank you very much. Bye.
Bye.